This is the PowerPoint presentation for the one-sample t-test. The objectives are: the student will be able to carry out right-tailed, left-tailed, and two-tailed one-sample t-tests. The one-sample t-test is used to answer the same research question that the one-sample z-test is used to answer. These questions relate to a single population mean. Questions such as, is the population mean greater than, less than, or different from some numeric value are answered with the one-sample t-test. Again, the one-sample t-test is appropriate when you have a single sample of subjects and the goal is to generalize from that single sample to the entire population. The one-sample t-test is more practical than the one-sample z-test. The one-sample z-test assumes that the population standard deviation, sigma, is known. However, in practice, it is unrealistic for us to think that sigma would be known. Therefore, we estimate sigma with S. When we do estimate sigma with S, the critical values for the statistical test must come from the t-table rather than the z-table. For very large samples, the t-test and the z-test are identical. This can be seen if you take a look at your t-table. The very bottom row of the t-table, labeled infinity, shows the critical values for the t with very large sample sizes. You should note that those critical values are the critical values from the z-table. Thus, for large samples, the t-test and z-test are identical. However, for smaller samples, the t-tests compensate for the uncertainty in parameter estimation, namely estimation of the population standard deviation with S. For smaller samples, the t-tests provide better critical values than the z-test. Therefore, the t-test critical values must be used for significance testing. The t-test statistic looks similar to the z-test statistic. The formula is x bar minus mu naught divided by s sub x bar. Note that s sub x bar is the standard deviation of the sampling distribution, or s divided by the square root of n. The degrees of freedom that determine the row of the critical value are n-1 for the one-sample t-test. Therefore, the t-test statistic for the t with n-1 degrees of freedom is x bar minus mu naught divided by the quantity s over the square root of n. When carrying out a hypothesis test problem, first you must determine h0 and ha. In this case, the null and alternative hypothesis will be mu equals some number versus mu is not equal to that number, mu is greater than that number, or mu is less than that number. Then you must select the appropriate test. In this case, we will be dealing with sample data that is used to estimate x bar and s. Therefore, the single sample t-test will be appropriate. The next step is to set the level of significance alpha, which will be set at 0.01, 0.05, or 0.10. Then the t-test statistic is computed as defined previously. After the test statistic is computed, there are two ways to draw a conclusion about the statistical test. The first way is to compare the p-value to alpha. This is the desired way when results are obtained using computer packages. When the p-value is used, the conclusion is reject if the p-value is less than or equal to alpha. Do not reject the null hypothesis if the p-value is greater than alpha. Alternatively, and especially when problems are computed by hand, a decision about statistical significance is made by comparing the test statistic to the critical values. The null hypothesis is rejected if the test statistic is more extreme than the critical values. The null hypothesis is not rejected if the test statistic is less extreme. Again, the decision about statistical significance can be made based on the p-value, which is much more common when results are analyzed with the computer, or by basing results on the comparison of the test statistic to the critical value, which is much more common when statistical tests are carried out by hand. We will address p-values further when we look at SPSS output. critical values will be used as the default method for all problems that are carried out by hand. After drawing a conclusion of the test using either the p-value or the critical value approach, which will always yield you to the same conclusion, you must draw the conclusion in the context of the problem situation. That is, talk about what is the meaning of the statistical test results. When drawing a conclusion based on the critical values, these three pictures illustrate the method. The critical values are the points that separate the reject region from the do not reject region. For a two-tailed test, that is, a test with a not equal sign in the alternative hypothesis, the alpha probability is split between the left tail and the right tail. Therefore, the t critical values will have probability alpha over 2 in each tail. When carrying out a left-tailed test, which is h0 mu is equal to some value versus ha mu is less than some value, the entire critical region or rejection region is in the left tail of the distribution. The critical value is the t-value that has alpha probability in the tail to the left. For a right-tailed test, the entire alpha probability is in the right tail of the critical value. Therefore, we reject the null hypothesis for very high values of the test statistic. When making decisions based on critical values, if the value of the test statistic falls in the rejection region, the conclusion is to reject the null hypothesis. Therefore, we will reject for large or extreme values of the test statistic. Otherwise, we will not reject the null hypothesis. When drawing a conclusion based on the p-value of a test, again, we have to consider whether we have a two-tailed or one-tailed test. The p-value is the probability in the tail of the test statistic. For the two-tailed case, notice that we have to consider the negative test statistic and the positive test statistic. The p-value is the probability in the tails of those values. For a right-tailed test, the p-value is the probability to the right of the test statistic, and for a left-tailed test, the p-value is the probability to the left of the test statistic. When making decisions based on p-values, the decision rule is if the p-value is small, that is, if the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null. A summary of the difference between the hypothesis testing using the one-sample z-test and one-sample t-test is found on this slide. Note the formulas for the one-sample z and one-sample t look similar. The difference is that in the one-sample t-test, the population standard deviation sigma is estimated with s. When we estimate sigma with s, our critical value must come from the t-table. Therefore, in practice, we use t-tests much more regularly than z-tests. Consider the following example. Numerous studies have shown that IQ scores have been increasing generation by generation for years. The increase is called the Flynn effect, and the data indicate that the increase appears to be about 7 points per decade. To demonstrate this phenomenon, a researcher obtains an IQ test that was written in 1980. At the time the test was prepared, it was standardized to produce a population mean of mu equals 100. The researcher administers the test to a random sample of n equals 16 of today's high school students and obtains a sample IQ of 121 with a standard deviation of 20. Is this result sufficient to conclude that today's sample scored significantly higher than would be expected from a population with mean equals 100? Use a one-tailed test with alpha equals 0.01. The first step is to state the null and alternative hypothesis. In this case, the null hypothesis, mu equals 100, versus the alternative, mu is greater than 100, is tested. The research question asks whether there is evidence that the population mean is greater than 100. Therefore, a right-tailed test with a greater than sign in the alternative hypothesis is appropriate. Further, the appropriate statistical test is a one-sample t-test. We have a single sample of data, and our research question relates to the population mean. In the problem, we are provided with the sample mean and the sample standard deviation. Because we have the sample standard deviation, we must use a t-test and get our critical value from the t-distribution. The test statistic is the t with 15 degrees of freedom, because our sample size is 16, is equal to x bar minus mu naught divided by s over the square root of n, or 121 minus 100 divided by 20 over the square root of 16, which gives us a test statistic of 4.2. The next step is to compare the test statistic to the critical value. Draw a picture and mark the critical value or values on the curve. For this problem, we have a right-tailed test, and we need to find the critical value for our test to make our decision. In this case, there are 16 data points, so we need to look at the t with n-1 degrees of freedom or 15 degrees of freedom. It is the t row with 15 degrees of freedom that our critical value will come from. The critical value is 2.602. Looking in the alpha 1 column probability of 0.01 and finding the intersection with the one-tailed alpha probability of 0.01 and the 15 degree of freedom row, we get the critical value of 2.602. We then compare that critical value to the test statistic of 4.2. The conclusion is reject the null hypothesis because our test statistic of 4.2 is greater than the critical value of 2.602. Thus, there is evidence that the mean IQ of today's students is higher than the population mean of 100. Note that decisions made based on p-values will be addressed when we evaluate SPSS output. Again, when computing problems by hand, it is sufficient to draw conclusions of the test based on critical values and the comparison of the critical value to the test statistic. A measure of the practical meaning of the size of effects is given by Cohen's d. Guidelines for interpreting Cohen's d are that 0.2 indicates a small effect, 0.5 a medium effect, and 0.8 a large effect. Cohen's d tells us the difference between our sample mean x bar and mu naught in terms of standard deviation units. Thus, a Cohen's d value of 0.2 shows a difference of 0.2 standard deviations, and that is classified as a small effect. A Cohen's d of 0.8 or even higher indicates a large effect. For a Cohen's d of 0.8, that would indicate that the difference between x bar and mu naught is 0.8 standard deviations, almost one full standard deviation. Again, that is classified as a large effect. For sample problem 1, the Cohen's d values is computed by taking 121 minus 100 divided by 20. That yields a Cohen's d measure of effect size of 1.05. This is a large effect. The mean difference between x bar and mu naught is over one full standard deviation. Consider a second sample problem. You are conducting an experiment to see if a given therapy works to reduce test anxiety. A standard measure of test anxiety is known to produce The second example is, research examining the effects of preschool childcare has found that children who spent time in daycare, especially high-quality daycare, performed better on math and language than tests than children who stay home with their mothers. Typical results, for example, show that a sample of 25 children who attended daycare before starting school had an average score of 87 with a standard deviation of 8 on a standardized math test, for which the population mean is 81. Is this sufficient evidence to conclude that the children with a history of preschool daycare are statistically different from the general population. Use a two-tailed test with alpha equals 0.01. The first step again is to state the null and alternative hypothesis. The null, h0 mu equals 81 versus the alternative mu is not equal to 81. Note we have a two-tailed test because the research question asks whether there is evidence that the population mean is different from 81. The appropriate test is a one-sample t-test. We have only one sample of data. Our research question is about a mean, and we are provided with the sample mean and sample standard deviation. This combination indicates that our critical value will come from the t-table. Our t-test statistic, x bar minus mu naught divided by s over the square root of n, is 3.75. To draw a conclusion, we compare that value of 3.75 to our critical values. The critical value comes from the t with 24 degrees of freedom. Our sample size was 25, so we look in the 24 row of the t-table. We are working at alpha of 0.01, so we have to consider the critical value that has alpha over 2 or 0.005 probability in the tails. Those critical values are negative 2.797 and positive 2.797. These serve as the cutoff points for our rejection region. We then compare the test statistic to the critical value and see that the test statistic falls in the rejection region. Therefore, our conclusion is reject the null hypothesis and conclude that there is evidence that children who attend daycare have significantly different scores than children who did not attend. Again, note that decisions made based on p-values will be addressed only when evaluating SPSS output. Considering the effect size for sample problem 2, we look at the difference between x bar and mu naught, 87 minus 81, divided by the standard deviation of 8. For this problem, the effect size is 0.75. Again, this indicates a large effect, a difference of approximately 0.75 or 3/4 of a standard deviation. This slide provides a link to running a one-sample t-test online. You can run this one-sample t-test only at an alpha of 0.05. The program does not allow you to alter the alpha. You have to provide the sample mean, the population mean, the sample standard deviation, and the sample size. When you run the t-test, you will get a conclusion of the test based on the alpha equals 0.05 level of significance. Again, the objectives were the student should be able to carry out right-tailed, left-tailed, and two-tailed one-sample t-tests.